So back to our problem that we were working on, problem 5 on the worksheet on potential energy and non-conservative forces. We launched a ball up at 30 meters per second, half-kilogram ball. We're putting everything that's described in the problem into our system and all the forces that are acting as internal forces. So the ball, the atmosphere, the gravitational force, the earth, they're all in the system. Gravity and the air resistance force that are acting on the moving parts of the system are also in the system. And our job is to find the maximum height above the launch point that the ball reaches if we're given that air resistance does minus 50 joules of work. So in this case, our system is everything. We're going to apply that most general so far work-energy relationship, where we keep all the non-conservative internal forces on the left-hand side. There aren't any external forces because we threw everything into the system. So this piece is going to be 0, but this is going to be that minus 50 joules, the work that's done by that non-conservative internal force. And associated with the gravitational force, we're going to have a change in potential energy. So let's put those in. Here's the minus, of course, this external forces, there aren't any, so that's a 0, but this internal non-conservative forces is minus 50 joules. Change in kinetic energy, we can always, without thinking too much, just write 1/2 mv final squared minus 1/2 mv initial squared. And in this case, initial is just after it's released, and final is when it reaches its highest point, so the final speed is 0. That helps us simplify a little bit there. And then the change in gravitational potential energy is mgy final minus mgy initial, and I have factored out the mg here because it's really y final minus y initial that we're after. That's the maximum height above the launch point. So this is the thing that we want to solve for, our variable. In this case, we can't cancel the m because there's no m on this side, but we know m, so that's okay. Doing the solution, plugging in m, v initial is our 30 meters per second, so this would be a 30 squared. We put in all of our m's, we put in g, and solve for y final minus y initial, and we get 35.7 meters. So that's the kind of problem that we could not have done with kinematics. All right, let's do problem 6 and 7 together. Problem 6 says a 2-kilogram block is given a 3 meter per second initial push on a rough horizontal table with a kinetic coefficient of friction of 0.3. Find the work done by friction after it has slowed to rest. So we're imagining we shove something, it's sliding across the table, and it slides until it comes to rest. How much work does friction do? First thing to realize is that we're expecting a negative answer. Friction is doing negative work the whole time. And we have some choices for what to choose for our system, but in this case, it seems simple enough to take our system to be only the block. That's a particle. And so, since it's a particle system that we've chosen, we can apply the work kinetic energy theorem. The only force that's doing work on the moving parts of our system, and that's our system is the block, well, there are 3 forces acting. The gravitational force, it's doing 0 work. The normal force, it's doing 0 work. But the friction force is doing negative work. So when this net work done by external forces, that's only going to be the work done by friction, and that's what we're after. So that's going to be our variable there. And we can calculate the change in kinetic energy because we know its mass, we know its initial speed, final speed is 0. So let's put those in there. The net work is just the work done by friction. That's what we're after. That's equal to the change in kinetic energy. The final kinetic energy is 0 because the final speed is 0, and we plug in the initial speed and the mass of the object, and we can solve for the work done by friction. In this case, it is negative, right? That's because we only have this term appearing here, which has a minus sign in front of it. Minus 9 joules. Notice that in that case, we didn't actually need this coefficient of kinetic friction in the solution to the problem. It didn't really matter. All it mattered in this case is that it came to rest. It might have come to rest really, really slowly if we had a very small coefficient of kinetic friction. Or if we had a very rough table, high coefficient of kinetic friction, it might have come to rest really quickly. And the answer of how much work friction does would have been the same in either of those cases. So it doesn't really matter how quickly it comes to rest. Problem 7 is a similar kind of problem. Again, a 2-kilogram block given the same initial speed of push on the rough table, same coefficient of kinetic friction. Find the speed of the block after it has moved 1 meter. So we're imagining it's sliding. It goes longer than 1 meter until it comes to rest, but we want to know its speed after it passes the 1 meter position from where it was released. And in this case, again, it seems simple enough to take our system to be just the block, so we can apply our good old friend, the work kinetic energy theorem. In this case, we're going to have to calculate. Again, there are 3 forces acting on the block as it's sliding. 2 of them do 0 work, gravity and the normal force, but the friction force does some negative work. And in this case, we're actually going to calculate that. And the V final, we're going to take our final to be the speed after it's moved 1 meter. That's going to appear in the change in kinetic energy. So the left-hand side, we're going to calculate as minus, it's a negative amount of work that's being done, and the way we're going to calculate the friction is that it does on the way from the initial to the final state is the friction force magnitude times the distance that it moves. So in this case, mu k is 0.3. The normal force is mg. It balances out the weight force, so 2 times 9.8. And the distance it moves in going from initial to final is 1 meter. So that's how much work is done by friction. Oh, I see, I dropped the ball in my solution here. I put a box around this, but I didn't actually solve for the speed. Well, how embarrassing. Let me try to verbally say how to do the final step of this. Once I've found that number, I set that equal to 1/2 m v final squared minus 1/2 m v initial squared. We know v initial. We want to find v final. So in that equation, I would just solve for v final with a square root. And that would be the answer to the problem. I got so excited, I guess, that I calculated that negative work that I stopped halfway through.